Let us take the second example. Analyze the beam shown in figure by stiffness method. If the supports B and C, that's mid support as well as right hand support, settles down by 2000 by year and 1000 by year. So there is a settlement of support which has been included in addition to the conventional gravity loads. So let us follow the same steps, whatever I have told in the problem one yesterday in the previous class. So we will follow the same step. The first step, you have to identify the local coordinates. That is, you have to identify what are the member end forces to be determined. So usually, I told you the member end forces which we have to determine during analysis is selected as the moments at the ends of the member. So if you take the member AB, the moment at the end A and B, that is like this. A, this is denoted by the coordinate 1 star, and moment at B is denoted by coordinate 2 star. So the positive direction is indicated by these coordinates. That is, clockwise is taken as positive, clockwise moment. So that is selected as the end moment is selected as the unknown to be determined. So that is your local coordinates or element coordinate. So that's the first step. You have to choose the element coordinates, or that is the unknown member end forces to be determined during analysis. That's the unknown internal forces to be determined during analysis. So that is unknown forces. We can represent it by matrix notation. That is this, corresponding to these coordinates PM1, PM2, PM3, PM4, or the moments which we have to determine during the analysis. It's a 4x1 matrix. That is what we have to determine. That's the first step. You have to formulate the element coordinates. Then second step, you have to find the kinematic indeterminacy, because it is the stiffness method of analysis. You have to determine the kinematic indeterminacy and represent the unknown joint displacements which you have to determine during analysis by global coordinate or system coordinate. So here, this problem, whatever is given, so the kinematic indeterminacy of this problem is 2. Kinematic indeterminacy means number of unknown displacements which we have to determine during analysis. So at each joint of the beam, there will be possible 3 displacements, that is horizontal displacement, vertical displacement and rotation. So all these 3 displacements are not there at joint A. At joint B, the vertical displacement is not there. Horizontal displacement, of course, it is possible because this is roller support. But this possible horizontal displacement, if it undergoes at joint B, then for the member AB, since we assume all members to be axially rigid, if this B undergoes a displacement horizontally, then A also should undergo, but A cannot move, so naturally B also cannot move. On similar lines, C and also that horizontal displacement will not be there. So out of 3 possible displacements, vertical and horizontal displacements are not possible at B and C also, but only rotation which is possible, and that is the unknown displacement which are possible and which have to be determined during analysis, and that I am indicating by the system coordinates. That is your second step, system coordinates. First step, element coordinates. Second step, system coordinates. That is unknown joint displacements. Unknown joint displacements to be determined. Displacements to be determined during analysis. To be determined during analysis. So this you have to identify. So first step, element coordinates, that is unknown member and forces that you have to determine during analysis, that you indicated by that matrix PM. And in the second step, unknown displacements, because analysis means it is evaluation of displacements, unknown displacements, as well as the unknown internal member forces. This is unknown internal member forces. Unknown displacements are these, that is ds, that is with respect to global coordinates. That is with respect to global coordinates, we have to determine these unknown joint displacements given and d2. That's what we have to determine. It is a 2x1 matrix. So these are the two things which we have to evaluate during the work analysis. That is the second step. So that means in the first two steps, actually what we have to determine during analysis, that we are indicating. What is that we are supposed to evaluate, that we are indicating in the first two steps. And of course, here we can evaluate what is known as member and fixed member and forces also. So you can assume each joint to be fixed at the ends like this. The member may be, whatever is there, we have to assume them to be fixed at the ends, not allowing any displacement. Then whatever loading is there on the member loading, whatever loading is there on the members, due to that load, we have to find the moment generated, fixed moment generated at the ends, and we have to find the equivalent loads acting at the ends of the members, not on the members. So whatever member load is there, that we have to replace it by fixed end action. So here, due to this load, the fixed end action will be WL by 8, and that will be 240 into 10 meters divided by 8, that is 300. They are the end loads or end moments corresponding to element coordinates. So here also it is 120 into that 10 meters divided by 8, that is 150. These are the end moments corresponding to these coordinates, fixed end actions. So that is PMF 1, it is 300, that is in the anti-clockwise direction. So it is opposite to this one direction, so it is minus 300. Here it is 300, then here it is 150 PM3, and PM4 it is plus 150. So it is due to the given extreme loading, what are the fixed end moment action that we have to take it. That also you can formulate here itself. The equivalent loads corresponding to element or the system coordinates. That also I am writing. Here I am writing PM, PMF. Likewise, here DS and PS I have to evaluate in the two steps. So here, this particular problem, it is not only subjected to loading, but it is subjected to a settlement of support also. So due to that settlement of support, what is the moment generated that we have to calculate. So here, A the Bn has settles down by 2000 by Vi, and likewise C also settles down by 1000 here like this. These two joints C, B and C, it has settled down by 2000 by Vi and 1000 by Vi. So due to this settlement, then again a fixed end moment generated here, and that also I have to take it as the fixed end load. So due to the fixed end moments, you know already from undergraduate class. So if there is a settlement of delta, then there must be a force here to cause that settlement, and that force will be 12 EI delta by L cube. So to keep it in equilibrium, there must be an equal and opposite force, and now this is in equilibrium with respect to all vertical forces is equal to 0, but it cannot be in equilibrium because these two vertical equal and opposite force will give a moment in the clockwise direction. To keep it in equilibrium, there must be equal and opposite moment here, and that moment will be 6CI delta by L square. So this is the moment generated, fixed end moment generated on account of this settlement of support. So here for EB, the fixed end settlement is 2000 by EI, that is delta is EI. So moment is generated along the coordinate 1. It is in the anti-clockwise direction. So that is, this is minus, I have to calculate that I have to take with respect to this coordinate 1, it is like this, and that value will be 6 EI into 2000 EI divided by L square, that is 10 square, so that value you will get as 120, and here also it is in the same direction, that is 120. Now, coming to this member BC, it has settled down by 1000 by EI, because C also settles down by 1000, B settles down by 2000, so the net displacement between B and C is 1000. So in here, instead of this delta value will be 1000 by EI for this BC. So moment generated is, of course, it is downward, here it is upward. So the moment generated is in clockwise direction. Here it is anti-clockwise, here it is clockwise, and that moment is 6 into EI into 1000 by EI divided by 10 square, and that value is 60 and 60. So here PM1 it is minus 120, PM2 minus 120, here it is plus 60 plus 60 because it is clockwise. So these are the moments generated corresponding to these element coordinates because of that settlement. That's the only change. Whenever settlement of support is given, you have to calculate the corresponding fixed end actions or fixed end moments due to settlement also in addition to the external loading. So the total fixed end actions will be minus 420, and here it is plus 180, here it is minus 90, here it is plus 90. That is your EMF, that also can keep it. Likewise, corresponding to 192, that I can call it as PS, that's the load, because the moment here, element coordinate as well as this global towards that they are coinciding, that one and the same, so I can use the same moment even here also. Here in the direction of 1, the total moment will be the moment corresponding to this 2 star as well as 3 star. That is, the moment corresponding to 1 will be 180, then minus 90. Corresponding to 2, it is 180. Corresponding to 3, it is minus 90. That together will be corresponding to 1. So corresponding to 1, the load will be 180 minus 90, that is plus 90. So this actually we take it as P joint load minus PMF due to the member loading. PMF minus PMF we take. If there is a joint load, that we can take it as it is, but due to member here in the global direction, I have to reverse this sign for the calculation of equivalent joint load. So previous class you saw a problem, that is overhang problem. Then due to that overhang there was a joint moment. That moment I was taking as it is, but here there is no overhang or any joint moment here at corresponding coordinate, that is straight away 0. So this is Pj is 0, PMS will be 180 plus minus 90, that is 90. That I have to take it as minus 90 because it is minus PMS. Then corresponding to 2, coordinate 2, here Pj is 0, there is no joint load. If there was a overhang, then the joint load would have been there. That value we were taking. Now the minus PMS corresponding to 2 load is 90. So that is load is, or here it is not 90, it is 210. 150 plus 60, it is 210. So here it is 0 is Pj, this is minus 210. So your PMS or PS is equal to minus 90 minus 210. So this much calculation you can do in the first 2 steps. The element coordinates and the internal member forces which you have to determine, that you have to indicate, along with the fixed and loading. Similarly, next in second step, you have to identify the system coordinates, that is what you have to determine the displacements, along with whatever the external load, equivalent load which is acting, that also you have to calculate. So these are the 2 steps which we have to follow. Then third step is nothing but unassembled stiffness matrix. Stiffness matrix. That is CM. So this unassembled stiffness matrix is nothing but the stiffness matrix of each member. Here given there are 2 members, AB and BC. So for 2 members, you have to work out what is the member stiffness matrix. That is stiffness matrix corresponding to element coordinates, and then that you have to arrange it, add all those things for the total structure here along the diagonal of the matrix, and that is called unassembled matrix. So the unassembled matrix, stiffness matrix, member stiffness matrix, that is stiffness matrix for the member AB. It is given by 2EI by L into 2, 1, 1, 2. This is the member stiffness matrix corresponding to element coordinate. That is standard one that you have to remember. In previous problem, here we made a mistake. Actually, we have taken some L by 2A or something. That correction I will introduce, that we incorporate in calculation of earlier problem. That I will give it here. That will please incorporate in the problem 1 and 2. There is no correction for step 1 and 2. Only step 3 there is a problem that I indicated. Please incorporate in problem 1 also. So here, EI value for AB, it is EI itself. So it is 2 into EI divided by L is 10 meters. So that 2, 1, 1, 2. Similarly, stiffness matrix of the member BC, that's also 2EI by L, 2, 1, 1, 2. EI value is EI itself, L is 10, so you will get it is equal to 2EI by 10, 2, 1, 1, or after simplification, it will be here by 5, 2, 1, 1, 2. Here by 5. So therefore, this unassembled stiffness matrix is equal to, which I have to arrange diagonally for all the numbers. So it is Vi by 5, I will take it outside. Then you have 2, 1, 1, 2. This is for the first element. So second element, it is 0 here. Here also it is 0. Then second element, it is 2, 1, 1, 2. So this is the unassembled stiffness matrix. That's what I have to calculate. So for the previous problem, so the correction which we have to introduce, I will give it here. So correction for problem 1, which we have given in the previous class. So that Km for that member AB, it is 2EI by L, where that EI value is 2EI, that was the value given, and length is 6, that 2, 1, 1, 2, I will take it, and that is 2EI by 3, 2, 1, 1, 2. That was the member stiffness matrix I should have taken. So I have taken that differently, is made that change. So for member BC, EI is EI itself, that is 2EI, L is 4 meters, and that is 2, 1, 1, 2. And this after simplification, you will get EI by 2 into 2, 1, 1, 2. That was the stiffness for the member BC in the previous problem, and the element, unassembled element stiffness matrix will be, so here LCM is 6, so I can take EI by 6 outside, and here since 6 is taken outside, this I have to take it as 8, and here it is 4, 4, 8, 0, 0, 0, 0. Here, since 6 I have taken outside, here this will be 6, 3, 3, 6. So this was the correction which you have to introduce for the calculation of this unassembled stiffness matrix in the previous example. Please incorporate this. So there was some mistake we committed while calculating the stiffness matrix of member AB and BC, and by calculating the unassembled stiffness matrix also. The rest of the things, so it has been taken care. So like the Ks and Ks inverse plate in the chain, you have to make it. Then finally, by doing the calculation, since I have given the answer correctly taken from the one which I have worked, so that error, it has been nullified there, only here you have to rectify it. Please incorporate that also. Since I am doing this step, I flash to the mind, I have given that particular. Please introduce that correction also in the previous example. Then the fourth step, after generating the unassembled stiffness matrix, you have to determine what is known as displacement transformation matrix. Displacement transformation matrix. Displacement transformation matrix. That is, or for generating the displacement transformation matrix, you have to apply a unit displacement. Unit displacement you have to apply successively along the system coordinates and determine the corresponding displacement along these element coordinates. While giving the displacement along one direction of the global or system coordinate, other displacement we have to restrain. That we have to take care. That's all. That means, in other words, to generate each column of this displacement transformation matrix, I had to go on giving unit displacement one at a time or successively corresponding to each of these system coordinates and determine the corresponding displacements again. No forces, only displacement corresponding to each. While giving displacement along one direction, displacements at all other directions we have to restrain. So that I will indicate it here by means of a sketch. So first here along direction 1, I have to give a unit displacement. That means here I have to give a unit displacement corresponding to this one direction. If I give a unit displacement, this will move up, this will come down, this I have to be straight. So all of the coordinates I have to be straight. This only I have to rotate, and all of this I have to be straight. So that means you get displacement only along here, equal to unity. So I told you have to give unit displacement along one coordinate, that is one system coordinate at a time, and determine the displacements generated along each of the element coordinates. So along coordinate 1, since I am fixing it, so displacement is 0. Along 2, it is 1. Along 3, it is 1. Along 4, it is being fixed, so it is 0. So therefore, the first column of this OR matrix, it will be 0, then 1, it is clockwise only, 1 here, clockwise, here it is 0. That is the first column of this OR matrix. It is as simple as that. So go on giving unit displacement corresponding to each of these system coordinates successively, and then evaluate the corresponding displacements along the element coordinate. So then you give unit displacement along coordinate 2, system coordinate 2, that is here, d2 equals 1, and restrain displacement along all other coordinates will restrain. So if you give a unit displacement here, then this will go like that. Here I am restraining. Here I am restraining. I already restrained is there. So I am giving unit rotation only with respect to that 2 direction, that is 1. So the corresponding element direction displacements, here it is 0, here 0, here also 0, here it is 1. Therefore, the second column of this rotation matrix will be 0, 0, 0, then 1. That's all, second column. So hence, for displacement transformation matrix, or it will be combination of these, that is 0, 1, 1, 0, 0, 0, 1. So it is a 4 by 1 matrix. So this Km Displacement Stiffness matrix is a 4 by 4 matrix, it's a 4 by 1 matrix. That's all. That is your fourth step. Third step, unassembled stiffness matrix, that is rotation. Then next step, fifth step, you have to generate structure stiffness matrix. Structure stiffness matrix. Yes. This structure stiffness matrix, by principle of contragradient, which I derived in the previous class, that is given by RT Km R. That is that. By principle of contragradient, I just derived this equation. So using that equation, straight away we can work out structure stiffness matrix. That is fifth step. So that is AS equals RT, R we have generated here. RT means transpose of this, the transpose of this matrix it will be 0, 1, 1, 0, 0, 0. That is RT. I will change the rows to column or column to rows. That is RT into Km. Km I have generated here. That is into EI by 5. This is 2, 1, 1, 0, 0, 0, 0, 0, and 2, 1, 1, 2. That is Km into R. R is again this. That is 0, 1, 1, 0, 0, 0, 0, 1. So this is RT Km into R. So if you multiply these two first and then resulting you multiply this. So that is, this is 4 by 4 matrix. This is 4 by 1. Here column equals row. So resulting matrix will be 4 by 1. And this is 2 by 4. So that 4 by 1 matrix here column is equal to row. So resulting matrix will be 2 by 1. So that means this KS matrix will be a 2 by 1 matrix. So that you can generate. So that matrix is given by, already I have the result. So I will straight away write the result. After multiplication of this, the result you are going to get here, Ks value, this EI by 5 into 4, 1, 1, 2. So that is a 2 by 1 matrix I told. So that's what you are going to get. This, if you multiply, you will get a 4 by 1 matrix. That 4 by 1. 2 by 4 into that 4 by 1, you will get a 2 by 1 matrix. And this is the KS, which is fifth step. So here itself, you can determine inverse of this KS, inversion of this KS matrix, which is nothing but 5 by EI into 1 over determinant of this is 8 minus 1, 7, and cofactor of this is 2, minus 1, minus 1, 4. So this is the 5 by 7 EI 2, 1, minus 1, minus 1, 2. That is the inversion of this stiffness matrix. 5 by 7 EI, 2 minus 1, minus 1, 4, minus 1, 4. That is such. So this is the fifth step. Then last two steps, 6th and 7th. So you have to generate the displacement ds that you have to determine, because I have told what are the things to be determined during analysis. One, we have to determine ds, another pm. So in the 6th step, we can determine the displacement. So the 6th step is find ds, whatever I have to determine. That first we determine, pm I have to determine. In 7th step, thereby the analysis is over. So there is no much other calculation, or only the matrix generations. Here you are generating PMS matrix, here you are generating PS matrix, here you are generating KM matrix, here R matrix, then you are performing matrix multiplication and transpose of the matrix, that you are doing purely only matrix operations. So that you are generating, then finding the inverse, then you can find out what is that unknowns. So for finding this ds, we can use that force displacement relationship in system coordinates, that is ps is equal to ks into ds. This also already I told, that is the force displacement relationship in global coordinates. Here we have generated already ks, ps is also we have generated, so that ds we can determine. Therefore, ds is equal to Ks inverse Ps. So either we can substitute Ps, Ks and ds with d1, d2, you can formulate a simultaneous equation, and that simultaneous equation you can solve by Gaussian elimination or Gaussian Cholesky method, whatever it is, or we can find the inverse of the matrix and we can do that. Either by through inversion we can evaluate, or by simultaneous equation solution we can evaluate. So in the next unit I will take those simultaneous equation and solve it. Here I will use Ks inverse because it is simple. So this ds is Ks inverse, which I have done here, that is 5 by 7 ei 2 minus 1 4 multiplied by Ps. Ps I got here, it is minus 90 minus 210. So this is a 2 by 1 matrix, this is a 2 by 2 matrix. Here column is equal to row, resulting will be a 2 by 1 matrix, and that is the displacement. And that displacement, we can multiply these two matrices, you will get the displacement as 1 over ei, 1 over ei into 21.43, 21.43, then here we get minus 535.71, minus 535.7, whatever it is. So that is the displacement, what we have to evaluate. So we have evaluated this. So then lastly, if I determine this PM of this over, whatever I have determined, I have indicated in the first two steps. Here, in the last two steps, 6 and 7, I am calculating that. So next, last step, 7th step, to find PM unknown and by then forces. For this, I can use this equation. We have PM, which is nothing but PM1 of this PM is given by PMU, PMF plus or KM, PMF, KM into Km into dm. So this is equal to dmx, this Km into dm. By principle of contradiction, dm is given by r into ds, r into ds. That's what we do. Yeah. So using that right away, you can work out the PM. So that is, this PM is nothing but PM1, PM2, PM3, PM4. That is the fixed elements. That is equal to PMF, which I have generated. That is minus 420, 180. Then minus 90, then 210, plus Km that we have already generated, that is Bi by R, and here by 5, 2, 1, 1, 2, 0, 0, 0, 0, 0, 2, 1, 1, 2. That is Km. All is 0, 1, 1, 0, 3 zeros, 1 r into ds. ds there I have calculated 1 over ei, 1 know what? AI into 21.43 and minus 530. This is 535.7. 535.7. So this here I will cancel. So this is 4 by 2, 2 by 1. So column and row are equal. Result will be a 4 by 1 matrix. Here it is 4 by 4. So here column equals row. Result will be a 4 by 1 matrix. So this is 4 by 1. So these two things you can add it. You will get this PM1, which is again PM matrix, which is again is 4 by 1 matrix. So that you will get it if you simplify this. I'll give you the final answer that is given by this is minus 415.7, then 188.6 minus 188.6. These two has to be equal and opposite because MBA plus MBC must be 0 and here I will get 0. Naturally, because it is simply supported here, there cannot be any momentum. C also has to be 0. This is what I am going to get. That is nothing but this. So with this, we have completed the analysis. In 7 steps, we are doing the analysis. So previous problem also same thing, except this correction, which you can incorporate. And of course, final answer I have given correctly. So that final answer, probably you may be wondering how he got it. That is, by making that correction, you will get that same solution. So we have solved these same two problems by flexibility method also. We got the same solution. You can verify it. So whatever we have worked in flexibility method, we are getting the same solution. So that means we are absolutely sure about our solution process. So with this analysis of beams, both when they are subjected to gravity load as well as settlement of support, it is completed. Next, we will take up analysis of truss. One truss problem, we will do it. That same truss, whatever we took for analysis by flexibility method, that same problem we will analyze. For again following the same 7 steps, we will follow and do that problem. And then one rigid plane frame problem, I found it. With that, this stiffness method of analysis also will be over. Now we will take up the truss problem straight away. Analyze the plane truss. We will take a truss problem. Third one, analyze the plane truss shown in figure by this stiffness method. So the same problem I have worked by flexibility method. So here we work it by stiffness method. So this was the truss taken. Loads 10 kilonewtons and 20 kilonewtons. This is 4 meters, 3 meters. This was the truss. And the area of cross section of vertical members, verticals. That is this member as well as this member. These are the two vertical members. And the vertical area of that vertical member is 2000 millimeters square, and area of cross section of other members, others, you can take it as 600 millimeters square, and EW, same as the previous problem, you can take it as kilonewton per millimeter square. For calculating the axial rigidity, AE, I have taken different area of cross section also same as previous problem. So this problem, let us solve by stiffness method. Same procedure you can allow. Of course, stiffness method is little bit cumbersome when compared to the flexibility method for stress problems, because here the kinematic indeterminacy is 4, that is 2 displacements here, and we join 2 displacements here. So totally 4 displacements, 4 unknown displacements which we have to calculate. Whereas static indeterminacy of this particular thing was only 1, which you saw in the previous example, flexibility method. Static indeterminacy was only 1, unknown was only 1 there. Whereas here, kinematic indeterminacy is 4 unknowns. That's why this is little bit cumbersome when compared to flexibility method. So that is why for solving problems, stiffness method you can use conveniently where kinematic indeterminacy is less. Likewise, flexibility method advantageously you can use where static indeterminacy is less. Usually for stress problems, so static indeterminacy will be weak. So flexibility method is most suited when compared to stiffness method. So let us follow the procedure. Same procedure. First step, you have to find out the element coordinates. That is, the unknown element forces what you have to determine during your analysis. So that is here, this we can take it as a hinge support. This also is a hinge support, and there are 5 members like this in the given problem. These are the 5 members. So these are the 2 vertical members. So always we will take the member forces which are purely axial forces, either tension or compression. We take tension positive always. This as the first member, that is first member force to be determined, that is member 1, and member 2 force, that is again tension, that is second member force. Then third member force is this horizontal member. Then fourth member force, that is this inclined member, that's again tension, fourth inclined member force, and fifth inclined member force, which is again inclined member. So these are the element coordinates. The element coordinates are nothing but the internal member forces which we have to solve during analysis. So that is PM, which we have to determine, or is PM1, PM2, PM3, PM4, PM5. These 5 internal member forces whose positive direction is taken by the coordinate with tensile positive, I have indicated. That's your first step. And of course, PMF is not coming into picture because there is no member load. On trusses are subjected to only joint loads and there won't be any member load. So that particular PMF is not there in this problem. Whereas previous problem, B problem, PMF was generated. Straight away we can go to second step. First step is only this element coordinates you have to identify and what are the internal member forces which you have to determine during analysis, that you have to indicate it. Then second step, the system coordinates. Let's say system or global coordinates. And that I have indicated. Here, this kinematic indeterminacy is 4. Already I told that 4 forces, what we have to determine, that you indicate it by this sketch or coordinates. So this is the truss like this, having 5 members and having 4 nodes, and we have to determine the displacement along this direction at this node displacement along this direction. That is coordinate 1, coordinate 2, here, coordinate 3, coordinate 4. That is horizontal and vertical displacement at these two nodes. Here, at these two nodes, these displacement, horizontal and vertical, they are 0 because they are in support. So the displacement is not there, only here. So these are the global direction displacements. This is global x and y direction I have taken. Or for this problem, straight away, I can take this joint as the origin, I can take this as the global x direction, this as the global y direction, x and y, and using this I can mark all the system coordinates. So here I have got load of 10 kilonewton, here I have a load of 20 kilonewton. So here system coordinates are is D, S, which there are 4 displacement, D1, D3, 2, D3 and D4, which we have to determine during analysis, PM, DS, what we have to determine during analysis, and the corresponding global nodes, I can take it. Here corresponds to 1, there is no load. Loads are all given directly in global direction. I can take that PS matrix. Here along direction 1, no load, along 2. So there is a 10 kilonewton load. Of course it is opposite to that positive direction of global direction I have taken. So it is minus 10 kilonewtons. So this I will convert it into newtons. That is 10 into 10 cube newtons. 10,000 newtons. So then here along 3 it is 0, along 4 it is again minus 20 into 1000 newtons. This is the global direction loads PS. So that is the 2 steps, first 2 steps are global. So I have to identify the element coordinates, member and forces to be determined during analysis, and the displacements in global direction, whatever I have to determine the system coordinate. I have identified the displacements to be determined, member and forces to be determined during analysis. Then third step, unassembled stiffness matrix. So it is similar to, and only to the stiffness, member stiffness matrix, the equation is changed. Whereas for beam and frame problem, it is 2EI by L, 2, 1, 1. That was the member stiffness matrix, which I generated my very first class. So here I will generate the Km for member 1, that is vertical members. First I will determine Km of vertical member, that is equal to AE by L. That's all. That's one value. Whereas B, it is 2EN by L, 2, 1, 1, 2. Therefore, truss members, the member stiffness matrix with respect to my local coordinate is just AE by L. Here, for verticals, A value is given as 2000 millimeter square and E value is given as 210 kilonewton per millimeter square, that is 210 into 1000. So many kilonewton divided by L. Length of the member, vertical member length is 3 meters. 3 meters. So this is nothing but you will get 10 cube into for all vertical members. So the stiffness matrix can take it as 14,000. Similarly, this Km for horizontal member, that is this member, that is given by A by N again. So A for horizontal member, it is 600, because it is area of cross section. For all other members, they say it is 600. E is 210 into 1000 divided by L. Length is 4 meters. It is 4,000 millimeters. So this you will get 10 cube into 31.5. That is the stiffness matrix of horizontal member. Next, K for inclined member. Inclined members. That's again A by N. So that is A is 600 10 E into 1000 divided by L of this inclined member, that is square root of 3 square plus 4 square, that is 5 meters or 5,000 millimeters, and that is equal to 10 cube into 25.2. That's what we got. Therefore, is unassembled stiffness matrix. Unassembled member stiffness matrix. It is unassembled member stiffness matrix. That is local coordinate. So all this stiffness we have calculated for all the 5 members. We have to arrange it along the diagonal. So I will take the 10 cube outside. That here for first member it is 14 and others around 0. Totally 5 members. Here 0. Then second member it is again 14. Second member is again vertical member. It is 1. Then second. That's again vertical member 14. So that's 0. Then third member, it is horizontal, for which stiffness matrix is 31.5. Then fourth member, which is a diagonal member, this, for which it is 25.2. Then fifth member, again it is a diagonal member, for which it is 25.2 into 10. So this is my unassembled members stiffness, unassembled member stiffness matrix full. So this is a 5 by 5 matrix, because 5 elements, 5 by 5 matrix. So 4 global coordinates, displacements are, unknown displacements are 4 by 1. Here it is member and forces are 5 by 1. So N is 5, N is this. So that's what it is. Then fourth step is that displacement transformation matrix. Displacement transformation matrix. That I have to generate. Displacement. So which I told, so to obtain this, each column of this transformation matrix, I have to apply unit displacement. Unit displacement successively along this global direction. You have to apply unit displacement, find the displacements corresponding to member coordinates. You will get the all columns of this. So there are 4 coordinates, along 4 global coordinates that give unit displacement one at a time and evaluate the corresponding forces. So that means it is a 4 by 5 matrix here put together. So I will give that particular displacement and show you here. First, I have to give unit displacement along coordinate 1 like this, d1 equals 1, and I have to restrain all other coordinates. So this all others I have to make it fixed. Only displacement it occurs only here, and that too only horizontal displacement, not even vertical displacement. So I have to make all vertical displacement 0 and only horizontal displacement at 0. So then I will get a displacement here in this member, because this is the displacement given like this. So this should oppose, there must be a force here, and that should be equal to 1 in the opposite direction, that is -1. It's the force in the direction of 3 in the opposite direction. So here I will get a force, and here there cannot be any force because it is in the vertical direction. So only I am giving horizontal displacement, vertically I cannot give any displacement. So here in this method it gives a horizontal component. So horizontal component like this itself. So here force in this has to be this way naturally. To give a horizontal component like this, to oppose this, so force should be like this. So that means this fourth member, force has to be in that direction, and that fourth direction is cosine component of this. So it is theta, if theta is the angle, then cosine of that theta, that is cos theta. Cos theta from this it is given by 4 by 5. Cos theta is adjacent side by hypotenuse. It is 4 by 5, so it is 0.8. So here I will get a displacement of 0.8. That I will give. And here and all, there won't be any force. Only in this member I will get a force displacement and no other displacement. So the arm here will be first member, it is 0, second member 0, so this is second member. Third member, it is -1 is the displacement. Then fourth member, it is again -0.8 cosine of the angle, and fifth member, it is 0. This is the first column of the R matrix. If this is understood, this is the major portion in this plus problem. Others are all easy. Only calculation of this displacement transformation matrix, yeah, it is a little bit tricky. You have to just be careful. For the inclined member, you have to take cosine of that. Whenever the horizontal displacement is given. Whenever vertical displacement is given, you have to take sine component. That's all. So, first displacement I have given, and second displacement, second global direction, I will give it in this fashion. So, D1 I have given, D2 in this direction. D2 equals 1. All other displacements, I will keep it restrained. So here when I give a displacement, here in this there must be equivalent opposite. It should be opposite. So here that should be opposite, and that is 1. That has to be. And here in this member it is horizontal. This member is horizontal, there cannot be any displacement. And here inclined member, I will get again a vertical component in this direction, because by compatibility the member end displacements has to be equal to the displacement at the joint. So here also vertical displacement component should be in the opposite direction, that is down. To give the displacement here, that displacement has to be in that direction, which gives you displacement in this direction. And this is nothing but, since it is vertical, sine of this displacement at the direction, sine theta. So this is theta. Sine theta is 3 divided by 5, that is 0.6. 3 by 5 is 0.6. Here it is 4 by 5 cos theta, there it is sin theta vertical. And this member is not there. Likewise, here displacement is 0, here displacement is 0. All other displacements and restrained. So, second column of this transformation matrix, force in the member 1, it is again opposite to this direction, so it is -1. Then force in member 2, it is 0. Force in member 3, 0. Force in member 4, it is -0.6. And force in member 5, it is 0. That is the element displacement, not force, displacement. Element forces are all. Then third direction, here the same press at this joint along this third coordinate, 1 over 2 over along 3, I have to give a unit displacement. D3 is equal to 1. D1 is 1, D2 1, D3 1. On same lines, here I have given unit displacement. Here it should be this way, opposite to that. Here also it should be this way only. So this is 1, this is cosine component, it has to be 0.8. Here of course it is vertical member 0. But all other it is 0. As I explained here, that becomes very simple. So here transformation matrix for member 1, 0, for member 2, 0 because it is vertical there, for member 3 it is 1. Like this, same direction. So it is +1, whereas here it is -1. I have taken here -1 because it is opposite. Here it has to be +1. Then fourth, it is 0. Fifth, it is again positive 0.8. Fifth member is positive 0.8. Here it is fourth member -0. Then lastly, I have to give unit displacement in the direction of 4. And give that. So here, upwards. D4 is equal to 1. D4 upwards. When I give unit displacement here, it must be a force here like this. Your displacement like this, here also this. So this is 1, it is down. So here in this gives a component in the downward direction has to be like this. So this is nothing but vertical component, sine means it is sin theta, it is 0.6. So here it is horizontal member, it is 0. So where the displacement is given, only these three are affected and other members automatically there won't be any displacement and it has to be 0. So naturally the fourth column, member 1, 0, member 2, it is member 2 direction opposite to that, so it is -1. Then member 3, 0, member 4, 0, member 5, it is minus 0.6. Minus 0.6. So therefore, what R matrix is nothing but you combine all these 0, 0, minus 1, minus 0.8, 0, then minus 1, 0, 0, minus 0.6, then 0, then 0, 0, 1, 0, then 0.8, then lastly is 0, minus 1, 0, 0, then minus 0.6. This is the displacement transformation matrix. This is only calculation which you have to be careful. That's only cos theta sin theta. You have to take from the different number. The direction, of course, it will be known. So only one joint you have to see where the displacement is given. Only those members meeting at that point where displacement is given, only those members displacement will be coming. In all others it will be 0. So that point you have to keep it in mind and carefully generate this transformation matrix. Then fifth step, of course, that is very simple. Fifth step, structure, stiffness, matrix, AS. So from by principle of contrarians, you have derived that AS is given by RT KM R. That is that. So by principle of contrarian, so you can use that formula straight away. Therefore, KS is RT, that is transpose of this. It is 0, 0, minus 1, minus 0.8, 0, then minus 1, 0, 0, then minus 0.6, 0, then 0, 0, 1, 0, 0.8, then lastly 0, minus 1, 0, 0, minus 0.6. This is that RT, transpose of that. So I converted this column to row, like that. That's an RT. Then multiply by Km, I have generated, it is 10 cube into, it is 14, 0, 0, 0, 0, 0, 0, 4. Then 0, 14, 0, 14, 3 zeros, then 0, 0, 31.5, 0, 0, and 0, 0, 0, 25.2, 0, 0, 0, 0, 25.2. That is the KM matrix, and R is this 0, 0, minus 1, minus 0.12, 0, minus 1, 0, minus 0.6, 0, 0, 0, 1, 0, then 0.8, and last column 0, minus 1, 0, 0, and minus 0.6. Now, what are the matrices which you have generated? I have taken here K matrix, R matrix. Now I have to do matrix multiplication and this. So this is a 5 by 5 matrix. So this is a 5 by 4 matrix. If you multiply row and column, they are equal. So resulting matrix will be a 5 by 4 matrix, 5 by 4 resulting matrix. So this, I have to multiply by this. So this matrix is nothing but, it is 5 5 by, not 5, 4 by 5 matrix. It is 4 rows and 5 columns. So here resulting will be 5 by 4. So column here is equal to row here. So resulting matrix will be a 4 by 4 matrix. So Ks matrix will be a 4 by 4. Naturally corresponding to 4 coordinates. So Ks matrix has to be a 4 by 4 matrix. So that I will give you straight away. The Ks matrix is given by Ks is equal to the 10 cube multiplied by, because the 10 cube is there, that I have taken there outside. So it is 47.63, then 12.1 and 0, then minus 31.5, then 0. So it has to be symmetric, 12.10 minus 31.5 and 0. Then this value will be 149.07. Then we will get 0, 0. So the symmetry is 0, 0. Then I have 47.5. This is also 47.53. And this minus 10.1 minus 10.1. So this is a 4.4 Ks matrix. That is for this entire structure. Stiffness matrix is that in the global direction. Then we lost 2 steps. That is, this is 5th step. 6th and 7th step, we are determining these unknowns. In the 6th step, I will determine ds. In 7th step, I will determine pm using the standard equation. Is that the problem is completed? So that is next 6th step to find ds. That's what I have to determine. ds. So use that force displacement relationship. We have the ds is nothing but ks into ds. P is proportional to d. Within the estimate of P is equal to kd, that's stiffness matter. I have generated all those things here. So all this ds is nothing but Ks inverse ds. Either I have to invert the matrix or I have to solve the linear simultaneous equation by putting ps value down. So that is nothing but. So here ps is known. Ps I have given at 0, minus 10, 0, minus 20. Ps it is known. So or I can use this equation. So instead of inverse, you can, I give it in the equation form and show that. This Ps is 0, minus 10, 0, minus 20. And of course, all these are in kilonewton, I have to multiply by 10 cube. Is there into 10 cube. That is equal to Ks, I have generated there, it is 10 cube into that matrix into Ps is d1, d2, d3, d4, which we have to determine. Now it is a linear simultaneous equation. We can solve it, solve for d1, d2, d3, d4. Straight away you can give this matrix into MATLAB and software, straight away you get the result. In the lab, here I am giving the procedure for generating the matrix. In the lab, you can just solve all these inversion, multiplication, all those things you can do it in the lab, each problem. Any complicated problem, you can do it on similar lines. So this value I have got straight away give you. So these values we get 10 to the power of minus 2 multiplied by this is minus 1.12 and minus 6.62, then minus 4.24, then minus 13.76, all minus 13. So many newtons, all these ones. No, not newtons, millimeters, all in same consistent units. Newton, millimeters. So displacement, they are all in millimeters. So I have evaluated this D. Then last step, we have to compute PM. And the problem will be over. That you are observing, only we are using matrices which we have generated. Then perform the matrix operation on the addition, subtraction, multiplication, division or inversion or getting simultaneous equation solved. That's all. So the last 7 step to find PM. So for this, I have already given the equation. This PM is nothing but, of course, for PM, because implied number is also there. You can use this straight away. AE by L is the stiffness matrix of any member. I am giving a general formula for any member, implied number. We have to take cos theta, sin theta. That's why here slight change is there. So that I am giving PM equals AE by L into U2 minus U1 into L. L is that direction cosine, cos theta or sin theta. Then plus U2 minus U1 into M. So straight away you can use this formula for calculating the force in any member having when axial rigidity value AE, length L and direction presents L and M. L is nothing but cos theta, M is nothing but sin theta of that member. Where theta is always measured in counterclockwise direction of any member having left hand 1, right hand 2, the displacements which we have determined for each member and we have determined here, D1, D2, D3 in global coordinates. This is U2, U2, this is U1, U1 left hand displacement, right hand displacement. So now I have determined these displacements here. D1, D2, D2, D3, D4, here they are all 0. Because it is suppose displacement is 0. So if you take any member, suppose if you take this member, vertical member, member 1, the displacements are this 0, 0, and here it is D1, here it is D2. This is member 1. AE value is known, AE by L, which you have already computed. Thank you, bit 14, straight away you can take it. And this U1, U2, E1, E2, that is known here. So this, if you take it as N1, N2, this D1, D2 is nothing but U1, U2. This is U1, V1. This is nothing but U2, V2. Displacement. That is known. And N and M are direction cosines. Cos theta here, theta is measured with respect to horizontal 90 degrees. So cos theta is cos 90 0. That is L is 0. M is equal to sin theta 1, sin 90. So M is 1. So like that for all the members, you can compute L and M, and these displacements are computed in step 6. You can find the member A forces. That's all. So the same procedure we do in the last unit, that is direct stiffness matrix, wherein we number the joints, number the nodes, then find all the element properties, direction, cosine, and all. So that of course will take it. So that same thing I have to apply for the this problem here for finding the member forces. So with this, the analysis of stress is done. So then last topic, one frame analysis I have to do, plane frame problem, probably I can do. Maybe tomorrow let us finish.